Right, good morning, guys. Today we're going to continue with projectile motion. For part of the lesson, you're going to be using an online simulation to collect some data and to plot a graph with it. But what we're going to be using that data to do is to check whether the simulation that I give you follows the laws of physics. So we're going to kind of derive a little equation to use first, and then we're going to check if that equation actually works on the simulation. So when I say the word derive, I mean we're going to start off from first principles, from kind of the most basic rules we know, and we're going to try and come up with a new equation that we can use. Okay, so the equation I want to come up with is one for the horizontal range that a projectile will travel. So if I want to know how far a projectile is going to go horizontally when I fire, say, a cannonball or something like that, I basically just want to get an equation that tells me that. Now, the equations of motion don't. I have to combine them and carry out a number of calculations. So we're going to start off, okay, considering a projectile that's fired at velocity v at an angle of theta from the horizontal. So you see this straight line leaving zero. Okay, this is my projectile. The projectile is going to follow a path, the curved path there, okay, but its initial velocity is going to be v, okay, and that's going to obviously be made up of a vertical part and a horizontal part. So we're going to do a number of calculations here to come up with our final derivation. All the time we're doing it without numbers here. So this is basically algebra. We're basically coming up with a formula for how we would work it out, and each formula then is going to be used to come up with another formula. So the first thing we're going to do is work out the vertical height that the projectile is going to go. Okay, because actually we need this in order to get to the next stage, So the height that a projectile is going to get to, we would use v squared equals u squared plus 2as. I'd rearrange it to give the vertical height. So this is s. I've put a v there just to show that we're only looking at vertical. And obviously, if I rearrange that equation, I get v squared minus u squared over 2a. Okay. Now, v squared is going to be equal to 0 because the final velocity when it reaches its maximum height is always 0. Okay, so I'm going to have 0 minus u squared. U squared is my vertical velocity. So instead of just using v, I'm going to use v sine theta. Or I've chosen to use u sine theta because we're looking at initial velocity here. Okay, and instead of dividing by 2a, the acceleration in this case is going to be the acceleration due to gravity, 9.81. So I'm going to put g in instead. It should be minus g, but the minus g on the bottom is going to be cancelled out by the minus u squared on the top. So they both should have minuses, but those two have disappeared. So this is my expression then that I can use anytime I want to find the vertical height of a projectile. And you've used it without even realizing when you've calculated these things in the past. Okay, because you've used v squared equals u squared plus 2as, and you've resolved the velocity into its components. So actually, you've put the numbers into this even if you didn't realize you had. Now we're going to use that vertical height then to work out how long the projectile spends in the air. And we're looking for a connection between time and vertical height. And I'm choosing this one here, s equals half at squared. Usually it would be s equals ut plus half at squared. Okay, but I'm getting rid of the ut term, okay, in this case, because I just need to know the vertical time that it's spent in the air, and it didn't actually start off with it didn't travel any distance at a constant speed beforehand. We're just looking at it slowing down. So I plug the numbers into this equation here then, for the fact that it's I can see some of you might get a bit confused by why I've chosen to drop this s equals ut plus half at squared. If you imagine that you dropped a ball from rest, okay, so you've got a ball in the air and you dropped it, it would have an initial velocity of 0. Okay, so you wouldn't worry about the ut. Now, in this case, it hasn't got an initial velocity of 0, but let's imagine it's falling. Okay, I'm kind of doing it backwards. I'm saying how long is it going to take to fall to the ground, and at the end I'm going to double that. Okay, it'll be the same amount of time to get to the top as it is to get to the bottom. So I'm going to do s equals half at squared. I'm rearrange that for t, which gives me 2 lots of sv over a. I'm going to substitute in the sv that we've just calculated here, so u sine theta squared over 2g, okay, and put that into here, okay. and then I'm gonna get to this formula here. Now that's the time that it takes for the projectile to fall from its maximum height. So all I'm going to do then is double that to get 2 lots of it in terms of the total time the projectile's in the air, because I didn't just want to know the time it would fall from maximum height, I want to know how long it takes to get there and to fall. Okay, and we're assuming in the absence of air resistance, which I didn't say here, but we are going to ignore air resistance, but whenever we use these equations of motion, that it's symmetrical. It takes the same amount of time to get to its maximum as it takes to get down. Okay, so hopefully that makes sense there. Right, next step. So we've now got the time it's in the air. Now we're going to use the time it's in the air to work out the range of the projectile now. Okay, so I'm just trying to move this photo across the screen. So the range of the projectile, because it's just traveling at a constant speed, if we ignore air resistance, we can just use velocity equals displacement over time. So I'm going to rearrange that for the horizontal displacement. It's just equal to the velocity times the time. The velocity, remember though, is just the horizontal component of the velocity. So that's going to be my initial velocity times cos theta. So u cos theta. Now I'm going to substitute in for t here from the time that we've just calculated, 2u sine theta over g. Okay, and I'm going to end up with something fairly complicated, u squared 2 sine theta cos theta over g. Okay, it's looking a bit of a mess. Now I don't know if in maths you've ever covered some of these kind of equations that link cos and sine functions, but 2 sine theta cos theta is exactly the same as sine of 2 theta. Okay, so I can actually simplify this a little bit using this mathematical relationship. If you've never done that in maths before, you could take my word for it, or you can look it up on the internet, but this, or even just plugs the numbers into a calculator to check it. But this is a real maths formula. Okay, so I'm going to put that in to here, and now I've got that the horizontal displacement, which is the range, is equal to the square of the initial velocity times the sine of 2 theta divided by g. Okay, which is almost where I want to be. Okay, now from that, okay, in terms of the range of the projectile, well, there's 2 things I'm going to get out of it. One, the maximum range is always going to occur when sine 2 theta equals 1, because anything inside a sine function, the biggest value it can take up is 1. Okay, so it could be anywhere between 0 and 1. So if I got the angle perfect, it would give me a value of 1. Now, the perfect angle for giving me sine 2 theta equals to 1 is when theta is equal to 45 degrees. Because basically, whatever's within the sine function, okay, to give me a 1, we want the sine of 90. The sine of 90 is 1, okay, the sine of 0 is 0. So I need what's inside the brackets to equal 90, and because it's sine 2 theta, okay, 45 degrees is going to be the angle that gives me the biggest value of this sine function, which is 1. Okay, so actually what this tells me is that the maximum range is always going to occur at 45 degrees. Okay, now that's fairly tricky. I'm not sure how your maths is at this point right now. Okay, but this equation is basically saying because of the sine 2 theta, that 45 degrees is the perfect angle to give the maximum range. So if I want the maximum range, I can just say sine 2 theta is equal to 1. And I can just say that the maximum horizontal range is now just u squared over g. Okay, I've called it v squared over g. Okay, at the moment, where v is just the initial velocity that we started at, and this isn't the horizontal or the vertical. This is just the overall velocity. So we don't need to resolve any components. We can now just say if I want to know the range of the projectile, it's always the initial velocity squared divided by g. And g is always 9.81 on the Earth. So we've now got, although we've had to go through all these kind of complicated steps here involving sines and cosines and squares and square roots, at the end we've got something quite simple, which is that the horizontal range, okay, is equal to u squared sine 2 theta over g. But if we assume that the angle is 45, okay, then the maximum horizontal range is just u squared, or v squared I've called it, over g. Okay, so you just need to know the velocity at which it's launched at, and you know that the maximum range is v squared over g, and that needs to be fired at a 45-degree angle. So what we're going to do, oh, by the way, I kind of would never expect you to go through all of this by yourself. Okay, although we might do all the individual steps in one go, I think this is a bit much for us at the moment. and you'll never be asked to do that on the exam. But hopefully, as we go through it, you can see that these are all kind of individually steps that you could do, okay, and that it leads us to quite a nice answer for the maximum horizontal range that's actually fairly simple compared to the steps we've gone through on the way. Now, what we're going to do is we're going to try and apply this equation to the online simulation that I'm going to show you and check whether the online simulation follows this rule. Okay, so I don't know if you guys have ever used this before. It's made by PHCT Bet. Basically, we can fire some projectiles at different angles and different speeds and different masses and different diameters, and we can include air resistance or not. And then we can measure things about that projectile, such as the time it takes to hit the ground or the range or the height it goes. So we're going to have a play around with this. The link to the simulation is in Google Classroom. I'm going to show you briefly how to use it and what we're going to kind of do with it. But before I do, okay, we've already got to this situation here where we've got to the fact that the maximum range is always going to occur at 45-degree angle, and that the range then will be equal to v squared over g if you use a 45-degree angle. So let's think about how we can prove this. Well, I'm going to rearrange this equation to give v squared equals g times s max, where s max is the horizontal range. And I'm going to compare this to how we can get a straight line graph out of it, because I'm going to get you to draw a graph, and I want it to be a straight line graph. Physicists always love straight line graphs. We'll talk more about why we do later, okay? But what I'm going to do is I'm going to say, well, if I want this to be a straight line graph, I need it to fit with a y equals mx plus c formula, because that's the formula for a straight line, where y is my y variable, x is my x variable, m is the gradient, and c is the intercept. Now, if I want to get a straight line out of this, I'm going to need to plot v squared as my y-axis variable, okay? I'm going to have to plot S max as my x-axis variable. And if I do that, I should find that the gradient m is g, and there shouldn't be any intercept at all. We should just get a y equals mx graph. There is no c value, no intercept. So what I'm going to be getting you guys to do is you're going to collect data on the simulation. You're going to plot a graph of v squared on the y-axis against S max, the maximum range, which is the range for 45-degree angle on the x-axis. And if you do that, and the simulation works as the physics says, then the gradient of your graph should be equal to g, 9.81, and there should be no intercept. Now, if it's not a straight line or the gradient's not equal to g, then we know that the simulation doesn't follow the laws of motion. Okay, so this is kind of your task. You're going to collect data from the simulation that will enable you to plot a v squared against S max graph. You're then going to calculate the gradient of the graph, and if it equals to 9.81 meters per second, then the simulation shows the simulation correctly follows the rules of physics. Okay, so let me show you the simulation. So here we go. We've got our kind of cannon here, and we can change the angle at which we launch things. Sorry, I've got all these things on my screen I'm trying to remove. So we can change the angle at which we launch things, and when we press the red cannon button here, for some reason there's a bit of a time delay on mine at the moment. When I press the button, it will launch a projectile out, but at the moment I seem to be waiting a lot. Oh, sorry, it has. It's just launched at such a low speed that we can't see it very much. So let's change that. Change it to 16. Press that cannon. Let's see what happens. Right, I've got some internet issues at the moment. It's very slow. And the cannonball will follow a projectile motion path. Okay, now just make sure. I don't know what when you first go onto it, whether this air resistance is ticked or not. We're going to remove air resistance because if I include air resistance here, notice when I launch again, we're not going to get quite the same results. And it should be that air resistance affects things not a lot, you can see here, particularly at speeds which aren't great, but it won't quite reach the same maximum height, and it also won't reach quite the same range. So we're going to ignore the air resistance because our equations of motion ignore the air resistance as well. If you want to get rid of any of the projectile motions you've already done, just press on this rubber and they should hopefully disappear. Mine's taken a long time to respond. You're going to be firing some projectiles, but because we're looking at the relationship between v squared and the maximum height, the maximum range, you've got to make sure that all your projectiles are launched at 45 degrees. Can we get there exactly? There we go. So every single one must be done with 45-degree angle, okay, and must be done in the absence of air resistance. You are going to change the speed, and for each speed that you use, and I want you to use at least 10 speeds. Okay, you can choose whichever ones they are. For each of these speeds, you are going to measure the range of the projectile. Now, in terms of how do you measure the range of the projectile, okay, well, there's a 15-meter target here. You can move it and it will tell you how far, or up on the top there's a tape measure. I think the best thing is this little box here. It tells you all kinds of stuff. If you put your projectile right in the middle of the crosshairs, it gives you the range. So this one, for example, has gone 19.98. So you're going to be changing your speed, okay? Don't change anything else. The mass shouldn't make any difference. The diameter shouldn't make any difference if there's no air resistance, okay? So these things actually shouldn't affect our experiment in the absence of air resistance. They didn't come into our equation. You know, when we were looking at how far it would go, mass didn't come into it, diameter didn't come into it. So without air resistance, those two are not going to be important. But don't change the angle, don't change the air resistance. Our independent variable is the speed, or at least we want the speed squared, and our dependent variable is going to be the range, which is the horizontal distance traveled. So I've linked for you on Google Classroom a little table you can put your results into. Okay, I've made these ones up, so they're not actually taken from the simulation. But you're going to choose 10 different velocities. Okay, you're going to work out what the velocity squared is. I've made mine really easy. I've used 1 to 9, so I've just squared those on here. Okay, and then I've made up a maximum range. Now you're obviously not going to make yours up. You're going to take yours from this simulation. Okay, now once you've done that, you're going to plot a graph, and we're going to use the graph to check that check whether it follows the rules of physics or not. So in order to draw a graph on Google Sheets, which is where your data is going to be, highlight your data, insert a chart. Sometimes it takes a while to come up, sometimes it doesn't. Now, the first thing we've got to think about when it turns up is it set up as we want? First thing, I don't like this having no points and just joining the dots, so I'm going to change from a line graph like they've drawn to a scatter graph. Yeah, okay, so go to the setup, and we're going to change to a scatter graph. We're going to insert our own best fit line instead. Now, I needed to have, if I just click back onto here, on the y-axis I wanted v squared, and on the x-axis I wanted s max. Okay, so is that the way round they've put it? Well, if you have a look at the values here, S max goes up to 164, which is this one. So they've put them the wrong way round because I've got because of what I highlighted. They don't really know. So I'm going to choose on the x-axis, instead of using the data from B, I want to use the data from C. So I need to click down there, and vice versa on the other one. I need to, instead of choosing C, I'm going to choose B. Okay. Now the graph looks basically the same shape, but it will affect the gradient. And if you've got your axes the wrong way round, you're not going to be able to check if the gradient is G or not. Now we need a title. I'll let you choose something on here. It's very slow at the moment, so we can call it graph to show how the velocity squared affects the maximum horizontal range. Okay, now also we need to have labels on the axes. You can just take what I've done on the table, okay, but the y-axis must be velocity squared, okay, which we measure, because it's velocity squared, we measure it in meters squared per second squared. Now on Google Sheets, it's not very easy to put this formula in properly, so I've used one of those little kind of hat arrows to show the meters per second, meters squared and second squared. It's not ideal, but it will have to do. And on the x-axis, this should be my maximum range, which is nice and easy in meters. Okay. Now at the moment, there is, so I need to click back on it because I need to give it a best fit line. So we're going to go and give it a trend line. To get a trend line, you go onto series, scroll down, and trend line. And the nice thing is it automatically gives you a linear one. Google Sheets is rubbish for any kind of trend line that's not linear, but for linear, it's okay. It gives me a decent best fit line through there. Now, next thing we've got to do is carry out a calculation to check if the gradient is equal to g. Now, I know mine's not going to be because I've just made up these results. So remember, gradient is going to be equal to change in y over change in x, rise over run, whatever you choose to do. And I want you to show your calculation in the box here, okay? So then my rise in this one is going to be 75 divided by 150. So it's going to give me, in my case, 0.5. We need units as well. Now, the units of velocity squared are meters squared per second squared, and we're dividing that by meters. So that should leave us meters per second squared, because we had meters squared per second squared divided by meters gets rid of one of them. So the good news about that is it gives us a unit of acceleration, okay, which is what we want because we're saying that our gradient may or may not be equal to g. So your job for this lesson is to collect the data from the simulation, to draw a graph of it, to calculate a g value, and then you're going to write down underneath, do you think that this simulation follows the rules of physics? Okay, any questions, then please send me an email or write down on the Google Classroom post. Thank you.